time we stopped here, we were looking at a low pass filter, a high pass filter design example. So what was the example saying? Example says we want a high pass filter. We know that the magnitude plot of a high pass filter looks like this, right? And the phase plot of the high pass filter will look something like this. This is the magnitude plot. This will be the phase plot. Without numbers, right? I mean, you can go back and you can go back and look at the numbers, but what they're saying is they have a high pass filter with a transfer function magnitude of minus 30 dB at 60 hertz. So the magnitude of the transfer function is minus 30 dB at 60 hertz. Okay. Find the break frequency for this filter. So they want FB, the break frequency for this filter. That the break frequency for a high pass filter, the magnitude is 0, right? So we said, and we know that this is a line with a fixed slope of 20 dB per decade, right? So at FB over 10, we expect to have a magnitude. So at magnitude of transfer function at the FB over 10 is equal to minus 20 dB. And the magnitude of the transfer function at FB over 100 is equal to minus 40 dB. So this is 1 decade away, this is 2 decades away, right? So we know that we are, and this is a straight line with a slope of 20 dB per decade, so we know that minus 30 is going to be 1.5 decades away from my break frequency. Right, so 1 decade away, it's minus 20 dB. 1.5 decades away, since this is a straight line that is connecting these 2 points, then at 1.5 decades away, I am at minus 30 dB. Everybody's okay with that? Okay, so if that's the case, then we go back to our definition of decade here from this slide, and we said that the number of decades is equal to log base 10 f2 over f1, where f2 is the high frequency, f1 is the low frequency. So a decade is a range of frequencies for which the ratio of the highest frequency to the lowest frequency is 10, right? So we know the number of decades now, which is 1.5, and we know the lowest frequency, which is 60 hertz, and they're asking us for the break frequency, which is a higher frequency, right? So we know this is 1.5 and f1 is 60, so we want to find f2, right? So we go back to our example. And we just substitute. So 1.5 decades, f1 is 60 hertz, FB is what we do not know, and we will be able to calculate FB from this equation. Okay, so we were able to calculate the break frequency of this filter. I can go a step further and tell you, okay, the resistor value is so and so. Find the corresponding capacitance value for this to make this filter, to realize this filter, right? You just substitute with FB is equal to 1 over 2 pi RC, which is what we derived for the low pass filter from the low pass filter equation. Next example. Before we go to the next example, actually, so just out of just for your sake of understanding, how do you know that this is a low pass filter and that this is a high pass filter? This is V out, and this is V in. Okay? Capacitors are what? Capacitors are open circuit for low frequency, right? So let's look at low frequency being generated by this source, DC to low frequency. So this capacitor will be an open circuit. So what's going to happen? The input will go straight to the output, right? And at high frequencies, the capacitor is more of like a short circuit, right? So at very high frequencies, this capacitor is more like a short circuit. So whatever you put in will be attenuated through this capacitor because it looks like a short circuit. So what's the voltage across the short circuit? Zero. So nothing will pass through, right? And in between them, of course, the capacitor will have some impedance, right? It will allow some to go through, some not to go through. Some will go through the capacitor, and some of the output will go straight to the output, right? And these are the asymptotes. No. Complete short circuit, complete open circuit. So this is why this is a low pass filter. How about why this is a high pass filter? Same reasoning. A capacitor for DC is an open circuit. For AC, it's a short circuit. So if I put low frequency source here, DC for example, this capacitor is an open circuit. Nothing will go through, right? How about if I put a high frequency source here? If I put a high frequency signal here, this capacitor is a short circuit. Everything at the input will go straight to the output. That's why this is a high pass filter. Okay? So this is, I just wanted you to sort of easily, okay, without even having to memorize, this is here, this is here. If you look at it, you should understand why this is the case. Okay, next example. You given an example here of a low pass filter, obviously, and we derived the transfer function for the low pass filter before, and it was 1 over 1 plus j f over fb, where fb was equal to 1 over 2 pi rc. Okay. Sketch the approximate straight line body magnitude and phase plus to scale of the transfer function. So you should be able to go, basically you go back to your circuit and take the values for the R and C that are given in the circuit and calculate FB. From 1 over 2 pi RC is equal to FB. FB is 1000 Hertz. You know that the low pass filter transfer function will look like this, right? This is FB and this is FB. If you go back to the transfer function phase and magnitude plots, the magnitude plot and phase plot that we've derived before for the low pass filter. So until FB, the asymptote is flat, so everything will go through. Beyond FB, it's 20 dB per decade, right? So you need to go, so the next decade after FB, so this is FB times 10, right? 1 decade later, we go down and the slope is 20 dB per decade, so this is minus 20 dB, right? They said, sketch them to scale, right? So to sketch them to scale, you should, sort of put all the numbers that you know about. So you put FB in there, everything until FB is 0, and then beyond FB it's a straight line with a slope of minus 20 dB per decade, and you go 1 decade later and sort of make sure that the slope is minus 20. Right, that's for the phase plot, for the magnitude plot. And for the phase plot, at FB, we're at minus 45 degrees. FB 1 decade before, it's 0, 1 decade later, it's 90 degrees phase shift. Right? And it makes sense that again, at high frequency, remember, at high frequency, everything is passing through the capacitor. Right? And capacitors, what do? They phase shift the currents and voltages with respect to each other by 90 degrees. Right? Yes. You had a question? No? No question? Okay. So it's really direct substitution, right? There's nothing. Next example. So they went a step after that, I guess, and you were given. They want you to realize a filter using an RC low pass configuration that has half power frequency. Half power frequency is basically the frequency at which FB occurs. So FB is the break frequency. It's called half power frequency or break frequency. It's where you have 3 dB in magnitude less. It's actually also where the power of the input versus the power of the output is half. So it has many definitions here. So given your half power frequency, or FB, is 1 kilohertz, and using a resistor of 1 kilo ohms, then you just substitute in FB equals 1 over 2 pi RC, right? Given FB and R, you calculate C. It's really simple direct substitution. Any questions on this example? The next topic is still another application. So another application of the frequency and magnitude plot, but it has sort of some physical significance. So we talked about bandpass filters before. It's a filter that allows a certain band of frequencies to pass. And we said that one way to do this is to put a low-pass filter cascaded with a high-pass filter. That's one way to do it. Another way to do it is using these resonance circuits. And resonance circuits, physically what resonance means is something that changes significantly at a specific frequency, like a physical phenomenon that changes significantly at a certain frequency. And it happens in all physical systems. So in electrical systems, what it means is it's a circuit whose impedance changes considerably at a specific frequency. So I can have what is called parallel resonance or series resonance. There are two configurations we will study. And in both configurations, what happens is the circuit contains some R's and L's and C's. At a certain frequency, the circuit will only look like a resistor. Right? So all the impedances of the capacitors and inductors will disappear. Same thing for parallel resonance. The circuit will only contain a resistor. The other impedances will disappear. What does that mean? So there's less impedance now for the current to flow. Right? There was current. That current was seeing an impedance, or impedance, which is a combination of some resistors and inductors and capacitors. At a certain value of frequency, the value of inductive impedance and capacitive impedance, they will equal each other, and you will opposite in magnitude. So they will disappear. And you will only be left with resistive impedance, with the resistance, which means that there is less impedance for the current to flow, so there will be more current at that resonant frequency, right? And this is something we can use for allowing a certain frequency or a certain signal to pass through. If I have a signal that has content at 50 hertz and 150 hertz, for example, and I would like only the 150 hertz to pass through, I can create a resonance circuit at 150 hertz. This resonance circuit at 150 hertz, for example, can either allow or damp. Depending on how I design it. But I can tune it such that at this resonant frequency, something happens, right? Specifically at this, so it will act like a bandpass filter in that case, right? So we will see what these circuits look like and how we design them. Okay, so series resonance. So series resonance is basically composed of, it's a circuit with R, L, and C components, and the impedance of the series impedance that this current is seeing is what? Is the combination of the R, L, and C. So it's R plus J omega L, or J 2 pi FL, minus J 1 over omega C, or minus J 1 over 2 pi FC. At the resonance frequency, what happens is that J 2 pi FL minus J 1 over 2 pi FC becomes 0. So these two terms become 0, and if they become 0, at this resonant frequency, I can solve for this resonant frequency. I can solve for F naught in this equation. And if you do that, you will find F naught equal to 1 over 2 pi square root of LC. Right? So at F naught equals 1 over 2 pi square root of LC, these two components, the inductive reactance component and the capacitive reactance component, will equal each other and will be opposite in signs, and they will cancel each other out at that frequency only. Right? So, which means what? Which means that at the resonant frequency, this L and C do not exist. They will not exist at this L and C at this resonant frequency. So this frequency, when it appears at the input, will appear across the resistor. Right? So I am allowing that frequency component only to pass through. For any other frequency component, this omega L is going to be very large, and 1 over omega C will be very large. It will have value. Right? They will have values at other frequencies, which means that the current at other frequencies besides the resonance frequency will be what? Higher or lower than the resonance frequency current? Will be lower, right? So it will be at any frequency besides the resonance frequency, I have the effect of the inductance and the effect of the capacitance existing, which means the magnitude of the impedance is high, so the magnitude of the current will be low. Current will be voltage divided by the impedance. So if the magnitude of the impedance is high, then the current is low. If these two components of the impedance, the 2 pi FL and 1 over 2 pi FC, go away, then the magnitude of the impedance is smaller, meaning the current will be larger for the same voltage. Right? So of course, if we look at what this, I'll go back to this slide. But what this means from a magnitude plot, remember what I'm looking at is what? The magnitude of my input. I would like to see what the magnitude of the input versus the output is at various frequencies, right? So I'm looking at the transfer function. So I'm looking at my transfer function. I would like to see my output. What will my output magnitude be versus my input at the various frequencies, right? So ideally what I would like to see is something that looks like I would like to see something that looks like this is my magnitude of V out over V in, which is my transfer function. Log or not, does not matter for now, right? But it's the output over the input. And this is frequency. If this is my resonance frequency, what do I expect to see across? This is V out. V out is equal to I times R. R is fixed. So at the point where current is maximum, I will expect to see V out maximum. When is current maximum? Current is maximum if this and this disappear. If there is less impedance through the voltage source to push current into the circuit, right? So I expect that at this frequency, which is my resonance frequency, which is equal to 1 over 2 pi square root of LC, that the magnitude here to be highest, and then elsewhere to be lower. Is it going to look like going to fall this way, or is it going to fall this way, or is it going to fall this way, and fall this way, or this way, or this way? This will depend on what? Yeah, specific values of L and C. Like many values of L and C can make this happen, right? So many values of many combinations of L and C can make this happen, right? So there has to be a way to sort of qualify the quality of the filter. If this is going to be a band pass filter that's allowing frequency within this band to pass through, is this a better filter or is the one outside a better filter? I just want to pass something around my resonance frequency. What is a better filter? The smaller one, right? This is a smaller one. If I just want something to pass through at the resonance frequency, then this smaller one is a better filter for my purposes. So there's what is called the quality factor that we define for such filters. And we define this quality factor as the ratio between the resistance in the circuit, the ratio between the inductance in the circuit to the resistance in the circuit, right? So defined in the next slide. So it's defined as the ratio of the reactance of the inductance at the resonance frequency to the resistance of the circuit. Why is the value of the inductance such an important measure? Because remember, inductance doesn't allow current to change quickly. So if you have a large inductance, then current changes will be slow. Right? If current changes will be slow, then your ability to filter will be worse. Right? If you think of it logically, right? Remember the inductor is like that current wheel, the water wheel, right? If you have a huge water wheel and this water wheel is full of water, like all the buckets of the water wheel are full of water. For you to change the flow rate, it will take time, because by the time you fill up all these buckets coming in a huge water wheel, it will take time. Versus if you have a small value of inductance, then you can sort of change, fill these buckets much quicker, and the flow rate will change quicker, right? So inductance, remember, VL is equal to L di by dt, and the inductance, the current of the inductor is equal to 1 over L, integral of the voltage with respect to time, right? So you're integrating the voltage that's on the inductor with respect to time. So for you to change the current, this integration takes time, right? So that's why we quantified, this quality factor as the amount of reactive inductance to the amount of resistance. Why to the amount of resistance? Because the resistance is what we have at the output when the circuit is in resonance, right? So ideally we would like this quality factor to be what? We would like to have a very narrow filter, as narrow as possible, and in that case, quality factor indicates the quality of the filter's performance. The larger QS, the better the filter performance. Why is that the case? Because L is actually in the denominator of your resonance frequency. So you would like this quality factor to be as large as possible. Time constant. Remember, the time constant of the circuit was what? Tau is equal to R over L, L over R, right? You would like the time constant to be as small as possible. So, right? You want a large quality factor for sure, yeah. Let me get back to the physical definition of it. But for now, so we will define quality factor as the ratio between the reactance of the inductance at the resonance frequency to the resistance. Why to the resistance? Mainly because it's what we have at the output. Okay? And then, if you solve for L here, you get an equation in terms of what? You get L in terms of what? You get L in terms of the resonant frequency and C, right? So I can solve for L here and substitute in this quality factor equation. And in that case, I will get a quality factor equation in terms of what? In terms of resistor and capacitor, right? So where this is coming from is solving for L here and substituting in this equation, right? So solving for L, so solve for L here and substitute here, you will get quality factor in terms of R and C and F instead of L and R. Okay? So if we look at the transfer function for the series resonance circuit, which is the output voltage is the voltage across the resistor over the input voltage, which is Vs. It's equal to the resistance, right? Output voltage is VR. So if we look at the series resonance circuit, so what is the output voltage equal to? The current times the resistance. How about the input voltage? Input voltage is equal to the current multiplied by the impedance by omega L plus IR plus I over j omega C, right? So the I in the output voltage is, and the I in the input voltage cancel out, right? So I look at, if I would like to do V output over V input, it's equal to I times R over I times R plus j omega L plus 1 over j omega c. So the i's cancel out, right? So the transfer function is r over r plus the rest of the series impedance. So this transfer function can be plotted here with respect to frequency. So the magnitude of the transfer function is plotted here against frequency, right? The magnitude transfer function is plotted against the ratio of, it's plotted against the ratio of frequency to f naught. Why is that? So that they can have, if f is equal to f naught, then this is equal to 1, then this ratio is equal to 1, right? So at 1, we know that this term cancels out. At f is equal to f naught, this goes away, right? And the r cancels with the r, and we're left with 1, right? So the magnitude of this transfer function will equal 1 at f equals f naught. And that's what they have here. So this is 1.0. This is the magnitude of the transfer function. And they drew it against f over f naught and on the x-axis, right? So this is the 1.0 here. Okay, so this they rewrote this in terms of quality factor. So they reordered the terms, etc., etc., and they used the definition for quality factor that we derived in the previous slide. So Q is equal to 1 over 2 pi f naught RC, and rewrote this down. So divided by R, so this becomes, divide by R top and bottom, so this becomes 1 plus 2 pi f naught L over R, and then minus blah blah blah, and simplify, and the idea is you should be able to write it in terms of quality factor and the ratio of frequency to resonant frequency, and resonant frequency to operating frequency. So at the resonant frequency, we see that the magnitude is 1, or reaches its maximum value. So again, it's nothing different from what we did before, except that we gave it some definitions, right? And we drew, instead of the x-axis being frequency, we drew the x-axis as the ratio of frequency to resonant frequency, just for our understanding, to clarify some physical phenomena that's happening, right? Okay. Some more definitions. So the distance between the half power point. So the half power point is defined as the point where the transfer function magnitude is minus 3 dB less. Right? Where is that happening? For the low pass filter, for example. If we go back to our low pass filter derivation, right? We saw that at the break frequency, right? At the break frequency, what was happening? At the break frequency, I calculated my magnitude. So at f equals fb, I am calculating a minus 10 times log base 10 of 1 plus 1, right? So the log base 10 of 2 is 0.3. 0.3 multiplied by 10 was the minus 3 dB. So this minus 3 dB point is this point here. This corresponds to what in the linear scale? If we go back to a linear, remember we did the linear scale and then we converted to dB, right, for the low pass filter. So this is the dB scale. The magnitude is in dB here, right? This is minus 3 dB. If we go back to the linear scale, for the low pass filter, at f equals fb, the magnitude was what? 0.707. Right? This is 0.707. Can everybody see this? 0.707. So at f equals fb, The magnitude was equal to 0.707. In dB, it corresponded to minus 3 dB. This point is called the half-power frequency point. That's why, if we look at our current example, here, they call this point here, where the magnitude on the linear scale is 0.707, they call this the half-power frequency point. Right? And they call this, so it's the point where the magnitude is minus 3 dB less. And this occurs at 2 points, of course, in the bandpass filter. So there's a lower half-power frequency point in the bandpass filter and a higher half-power frequency point in the bandpass filter. And these occur at an equal distance from the resonance frequency. So the high frequency half-power point is the resonant frequency plus the bandwidth over 2. The bandwidth is the distance between these 2 points, right? And the lower half-power frequency point is the resonant frequency minus the bandwidth over 2. And the bandwidth is defined as the difference between higher half-power frequency point and the lower half-power frequency point. And it's also defined. It can also be defined as f naught over the quality factor. And the derivation for this is not something you need to know. It's a definition. Okay. So now we will do an example. So we have a series resonant circuit that is acting as a as a bandpass filter. They would like to do what? Find the resonant frequency. And the resonant frequency is from this equation, 1 over 2 pi RC. They want us to find the resonant frequency, and find the bandwidth, and find the half-power frequency. Assuming the frequency of the source is the same as the resonant frequency, so this is supplying the source a signal at the same frequency as the resonant frequency. And they would like you to find the phasor voltage across the elements. So after you find the current, you multiply the current multiplied by the impedances at the specific frequency, and you find the phasor voltage across the elements. And then they want you to draw the corresponding phasor diagram. Right? So the half-power, the resonant frequency is calculated from this equation. So it's 1 over 2 pi square root of LC. You're given an L of 159.2 millihenry. You're given a C of 0.1592 microfarads, and an R of 100 ohms. You substitute in this equation, you will find the resonant frequency. The quality factor equation is what we talked about before, 2 pi FL over R. You substitute and find the quality factor of this filter. Knowing the quality factor and the resonant frequency, I can calculate the bandwidth. Remember, the bandwidth was this distance here. So it was F high. It was the today is not a good day. This is the high frequency half power point, and this is the low frequency half power point. The difference between them keeps resetting. Anyway, the difference between them is the bandwidth, and we saw the bandwidth, the equation for the half power frequency point, and the lower frequency half power frequency point, and the higher and lower frequency half power frequency point, and those were equal to the resonant frequencies plus minus half the bandwidth. So any questions on this? So what did they ask for next? So we calculated the bandwidth, we calculated the resonant frequency, and they would like you to do what? Calculate the phasor voltage across the elements. right? So how would you calculate the phasor voltage across the elements? We have the voltage of the source. V is equal to IR at the resonant frequency. At the resonant frequency, the output voltage here is equal to what? Equal to the input voltage divided by the resistance, which gives you the current. And then you take the current, multiply it by this 100 ohms, and will give you the voltage across this element, right? But you calculated the current on the way, right? Because this voltage divided by this resistance is the current at the resonant frequency. So you know what the current is at the resonant frequency. So you take that current and you multiply it by j omega L. And this will be the voltage across this element. And you multiply it by 1 over j omega C. And this will be the voltage across this element, right? So let's see what they did here. So at resonance, the impedances are, so at the frequency they calculated ZL, which is j omega L, and they substituted the value of L, and it's j 1000 ohms. They calculated ZC, it's also minus j over 1 over 2 pi FC, minus j 1000, right? So these impedances, they have values, it's just that the values are equal and opposite at the resonance frequency. So the sum of the three, the R, the L, and the C impedances will make these two vanish at the resonance frequency. So hence the total impedance at resonance is R plus ZL plus ZC. If you do the summation, then the total impedance will only be the 100 ohm resistance at the frequency, at the resonance frequency. So we will calculate the current. So the phasor current becomes what? The current is equal to the voltage of the source divided by the impedance at resonance. The impedance at resonance is equal to the resistance only, right? So that's why we took 1 angle 0 divided by 100. So it gives us a 0.01 angle 0. This is the current at resonance. And they're asking you to calculate the voltage across the other elements at resonance. So the voltage across the other elements at resonance is what you see below. So the voltage across the resistor is the resistance times the current. So the resistance 100 ohms times 0.01 with an angle 0. So we expect to see 1 angle 0. And across the inductance, we go back to the ZL that we calculated at the resonance frequency, J 1000 ohms. So J 1000 times the current that we calculated at resonance is 0.01 angle 0. So it's 10 angle 90. And this one was 10 angle minus 90. So we can draw all three on the phasor diagram. So this is the voltage across the resistance here, and then the voltage across the inductance is 10 angle 90, and the voltage across the capacitance is 10 angle minus 90, right? And it makes sense that these two are equal and opposite in magnitude. They will vanish. They will go away at resonance. So this is the phasor diagram for the voltages across the elements. So any questions on this? Pair resonance is exactly the same. So, but just the equation is a bit different, right? So the equation for the impedance. So here, how do you add impedances in parallel? So 1 over Z equivalent is equal to 1 over the impedance of each branch, right? So if you bring this 1 over Z here, it's equal to the impedance